Hello everyone. Welcome to the SWAM NPTEL course on Mathematical Geophysics. We continue with the third module, Mathematical Modeling Part 1. Today we are going to discuss the lecture number 2, that is Gravitational Field. In this lecture, we will cover some very basic elementary concepts related to the gravitational field. The gravitational field, as we have discussed in earlier lecture, forms one of the most important fields in geophysics. Thus, the following components will be discussed in the present lecture. First, the Newton's laws of motion, the Newton's law of universal gravitation, and then the Newton's law of attraction. Then we will have a discussion on comparison between Newton's laws of motion and gravitation. Then we will discuss the concept of elementary mass. And lastly, we will discuss various applications of the gravitational field as inherent in geophysical studies. So let us begin. First, the Newton's laws of motion. The Newton's laws of motion is a familiar concept for many. The Newton's laws of motion describes the motion of an object and the forces acting on that object and the resulting interaction among the body and the forces. The fundamental laws are three in number. First, the law of inertia, which states that an object will remain at rest in absence of any external forces, and it will continue to move at a constant velocity unless an external force disturbs it. The second law of force and acceleration. The acceleration of an object depends on the mass of the object and the net force acting on the object. This is mathematically represented as A vector equals the force by mass. In other words, force equals mass into acceleration. This is the common form of the Newton's second law, as we have used in many previous applications, as we have used in many earlier studies. The third is the law of action and reaction, which states that for every action there is an equal and opposite reaction. Mathematically, it can be represented as F12 equals minus F21. This can be read as the force acting on 1 by an agent 2 equals negative of the force acting on agent 1 acting on agent 2 acting as negative of the force acting on 2 by agent 1. Mathematically, this can be read as the force acting on body 1 by agent 2 equals minus the force acting on body 2 by agent 1. Thus, the Newton's laws of motion, a familiar concept, is reviewed here for completeness. What are the focus? Next, we discuss the focus and applications. Newton's laws of motion generally applies to all types of motions, such as the motion of cars, projectiles, falling objects, etc. This forms the basis of classical mechanics. Next, we consider the Newton's law of universal gravitation. The Newton's law of universal gravitation forms the fundamental basis of the gravity and other associated field studies in geophysics. The Newton's law of attraction explains the gravitational attraction between two masses located at a particular distance. For example, have a look at this picture. A and B are two locations where the center of masses capital M and small m are located. O is the origin. R is the distance between point A and point B, which are the centers of the masses. R is the distance between point A and point B, which are centers of the masses. The Newton's law of universal gravitation describes that any two objects with masses attract each other. The force of attraction is proportional to the product of the masses and is inversely proportional to the distance between the centers. This is mathematically represented as F equals minus capital G multiplied by m into capital M divided by r square. As the force is directed along the line joining the centers, that direction is denoted by the radial vector r vector. The r vector is directed along the centers of the 2 points. F is the gravitational force, G is the gravitational constant, which is universal for all materials. G equals 6.67 into 10 to the power minus 31 meter cube per kg per square of the second. M1 and M2 are the two masses and R is the distance between them. This is the very familiar law of gravitation proposed by Newton for two objects which have their centers at a distance of r between them. This law specifically deals with gravitational interactions, and this law has been used to explain the planetary orbits, satellite motion, tidal forces, and many other applications in planetary sciences as well as geophysical studies. Next, we look at the Newton's law of attraction. Now, Newton's law of attraction combines two forces. As planetary bodies have mass, but they also undergo rotation. So, the net force at any point is the combination of the gravitational force and the force generated through rotation. Thus, the gravitational method is a study of the distribution of Newton's attraction force, which is capital F, caused by all masses of the Earth under the influence of the rotation. One part of this Newton's attraction force is the uniform motion around the rotational axis Z. The other part is generated by the weight itself. So the total Newtonian force is given by F vector, which is a combination of centripetal force and the force generated by the gravity, that is the weight of the object. The centripetal force is directed towards the rotation axis. In this figure, we can see this clearly. The z-axis is the axis of rotation, which is occurring at a rate of omega. The centripetal force on any object is directed towards the rotational axis and perpendicular to it. This is the direction of centripetal force. Note that the centripetal force does not act in the same direction as the gravitational force, which is along the blue line. This is the total Newtonian force. P is the weight of the object. Vectorially, this diagram can be represented as BO vector equals AO vector plus BA vector. The centripetal force Fa can be calculated and removed very accurately, and the remaining force, which is P, is used for further geophysical analysis. Thus, the Newtonian law of attraction encompasses the effect of rotation on top of the gravitational attraction for geophysical applications. Now, let us have a detailed comparison between the fundamental effects between the fundamentals of Newton's law of motion and Newton's law of gravitation. The Newton's laws of motion and the law of attraction is compared on the basis of four characteristics. 1. The general focus. Newton's law of motion deals with general forces and interaction between the general forces. It is not restricted to gravitational field only. It includes electromagnetic forces, friction forces, and all other types of forces which may be conservative or non-conservative in nature. However, Newton's law of attraction deals with gravitational force only. As far as the Newton's laws of motion are concerned, it governs the motion of various bodies which may or may not be following the conservative field characteristics. But the Newton's law of attraction only deals with the conservative field, which is the gravitational field. Next is the mathematical formula. The mathematical representation of Newton's laws of motion is elegant and general, which is F equals to ma. The acceleration can be generated by any force field such as gravitational field, electromagnetic field, friction field, or any other force field, and the action on the mass m will be given by this equation. The Newton's law of attraction is restricted to gravitational interactions only, where F vector equals minus g m1 m2 by r square directed along r vector. For Newton's laws of motion, the direction of the force and attraction is obtained from the vector sum of all applied forces. Next, we consider the nature of the law. The Newton's law of motion explains motion due to forces, whereas the Newton's laws of attraction explains the attraction between masses. So, the nature of Newton's law of motion is more general compared to the Newton's law of attraction. The applicability of Newton's laws of motion is vast. It governs the motions of vehicles, falling objects, any macroscopic object undergoing classical mechanics. The Newton's laws of attraction governs the motion of planets, weight, tides, etc. Next, we look into the concept of elementary force. Consider two elementary masses m1 and m2 positioned at q and p respectively. The distance between these 2 points is LPQ. Consider an elementary force dF acting at a point P. The mass are m1 for Q and m2 for P. The dimensions of volumes of two elementary masses are much smaller than the distance between them. Hence, they can be understood as point masses. The elementary masses m1 acts on the elementary mass m2 with a force dFp along the unit vector LQP. This unit vector is directed from P to Q, and is proportional to the product of the two, and the force is proportional to the product of elementary masses and inversely proportional to LPQ square. Thus, the Newton's law of attraction gives us this relation that the elementary force is proportional to m1 m2 by Lp square. The proportionality constant is g, and since the masses attract each other, hence the minus sign. Note that to indicate the direction, Lp vector is introduced with the denominator now being Lpq cube. The g is the universal gravitational constant and is proportionality constant for the force and the masses, where g is the universal constant equals to 6.67 into 10 to the power minus 11 meter square per kg per second square. Now the properties, now we will have a discussion on the various properties of this elementary force. The mass m2 acts with an elementary force on m1 given by dfq, which is minus gm1 m2 by lpq. Note the change in the notation of lqp to lpq, as the df is now related to q. LPQ and LQP are magnitude-wise same but directed antiparallelly. Hence, the forces are also antiparallel to each other. These forces represent the action of one elementary mass on another and vice versa. Thus, the elementary forces between the elementary masses are antiparallel forces. Next, we consider the various applications of the gravitational field in geophysics. First, we look at the concept of gravitational field for an elementary mass. This is required to understand the fundamental characteristics of the gravitational field in geophysical applications. The force dF for P is proportional to the elementary mass m2p. This is subject to the action of force from This is subject to the action of this force. Next, we discuss the concept of the gravitational field for an elemental mass. This concept of gravitational field for an elemental mass is very useful to understand the fundamentals of the gravitational field theory in geophysical applications. We take help of the same picture which we had discussed in previous slide. The force dFp is proportional to the elementary mass m2p. Thus we consider the ratio dGp, which is given by the dGp is nothing but the gravitational force per unit mass. This is also given by minus g into m2p by lqp square directed along lqp. Thus, the dgp acts somewhat like a potential. This potential is nothing but the gravitational field at point P. This gravitational field is caused by the elementary mass m2p. These are the field lines of the gravitational field around m2p. Next, we consider the concept of gravitational field for a distribution of masses. The distribution of masses is a very important concept in geophysics as the planet and other bodies in the solar system are not homogeneous material. A planet or any other geophysical rock samples is composed of various different type of elementary and compounds, various different kinds of elements and compounds which have different densities. Hence, the masses have a various and hence the distribution of masses. Thus, assuming that instead of elementary masses, we have a volume V, which is nothing but a distribution of masses. These are the masses which construct the volume V. The total mass can be obtained as an integral rho q dV. The gravitational field caused by the elementary mass is given by dGp. Integrating the gravitational field for all the masses using the integration gives the total gravitational field caused by the distribution of masses. Thus, we have the gravitational field G vector due to the point P as minus G integral rho dV by LPQ square LQP. This is integrated over the entire volume V. So this gives the overall gravitational field for a distribution of masses instead of a point mass. Using this concept, the gravitational field of subsurface elements or subsurface distribution of various masses can be obtained for geophysical applications. For example, if this is the surface and these are various point masses, the combination can be understood as a distribution of mass. If the cross marks is the ambient low density material with the square denoting high density material, the combined effect of all these point elementary masses results in the gravitational field due to a distribution of masses. This is extremely important for various geophysical exploration applications which we will consider in further lectures. Thus, in this lecture, we obtain the following conclusions. The gravitational field, in particular, can be used to study Earth's internal structure and composition, various, various geological processes such as mountain building, earthquakes, and volcanic activity. These processes somewhat give a distribution of masses which vary with space and time. Hence, this leads to the gravitational field, which is complicated spatially and varies temporally. The interaction of these individual components along with their masses results in complicated gravitational fields. Although the processes are very slow and the gravitational field does not change rapidly. The gravitational field is also affected by the global environmental changes, sea level rise, and ice sheet dynamics, which are very exciting topics in geophysics related to gravitational field. One can refer to the following book for further understanding. Thank you.